我先上个。Hello. Yeah. Good afternoon, everybody. So, hi, Guitars. How are you?
I'm fine. How are you?
Good. Yes. I just updated Zoom and how to make your co-host. Oh, it's here. Yeah, now you are the co-host. Please help me admit people in the session. So, oh, well, I think the the Zoom looks prettier. However, I'm a little bit unfamiliar of what things are. Okay, yes. Okay, anyway, it's good. We are recording, right? Okay, yes, it seems to be so. Yeah, hello everybody. I hope you have a fruitful and enjoyable student vacation. So welcome back. We still have people join. Yeah.
Hi, Jun. Can I ask questions?
Yes. I just
Okay.
was about to say if you have questions, we can take this few minutes.
Right. Yes, actually, we got video assignment 2. Just wanted
2 or 3?
2.
2, okay.
Yeah. So I double check. So how many data sets do we need? Like 1 or 2 or 3?
You will need to okay, for the full mark. Yep. You will need to run the algorithm on 4 data sets. They have 2 parts. You need to run the algorithm on 2 different
training data sets.
Yeah. And for each of the data sets, we need to split that into training and test. Right. So totally there are 4 tests needed, but that is to say you want the full mark.
Yeah.
Our focus, yeah, full mark, 100% without any deduction. You get the completely best result. But our focus is on the algorithm itself. We did not focus on practical applications. Therefore, it is acceptable if you only run the algorithm on 1 data set and split the data set into 2 parts. That is also okay. The points associated with the second data set is not many. I think maybe 3 or 2 points at most. Okay.
Right. Okay. And that introduced my second question. So, as you mentioned, we have to split the data set into training and testing. Can I use the function from scikit-learn, the train test split function, to split out the data set into training and testing? Is that okay?
Yes, you can. Yes, you can. But wait, because I have pinned myself the video. I don't know your name. Anyway. Yeah. Because it's a recording. Sometimes I want the recording to be okay. I'm present on recording. Doesn't matter. Okay. Anyway, yeah. So the thing is, I answered simply yes. But you ask me that question indicates you did not review the previous discussion, and we have because that question has been asked for maybe several
times.
Yeah, and we have discussed that. I would strongly recommend you to review the previous discussion because we also discuss other aspects of the assignment. So right. I think most of the discussion happened in session 5. Yes, session 5.
The one that you show us the HD example. I think it was session 5. Yes, yeah.
Session 5. Yes.
Okay.
Yeah.
Right. Okay. Thank you so much. I have like a review. Thank you.
Okay.
Hi, I have a question. So if I were to choose the perceptron model, in your example, the guy chose the decision tree and like extend it to like random forest. So should we develop the perceptron to like multi-layer perceptron or just
Oh, yeah, I got the question. You mean if you want to make a complicated model of a complicated ensemble model, is it allowed to use third-party implementation of the weak classifiers? Is that correct?
what I want to ask is should we develop it more, or the report only need like just a perceptron model is good enough?
Just one model is good enough. Just one is okay.
Okay, thank you.
Yeah. There is a related question, and that will be addressed today, but I can bring the point up here. Today we will learn ensemble models. To implement ensemble models is just a fancy name of, okay, if I have a group of simple models, the models that we have learned, such as decision trees. However, none of them are strong enough for my task. So I want to collect them and let them vote, or let them vote in a more systematic way, whatever. I design a system to make a committee from those weak predictors. Therefore, I can achieve better performance whatsoever. We will discuss later. And the question was, one open question was that, if I'm going to implement such a system in my assignment 2, am I allowed to use third party, such as scikit-learn or whatever library? Can I use a third party implementation for my weak simple models? And the answer is yes, you can. So because the focus of ensemble models is about the systematic way of let the weak models built up and vote. So from this viewpoint, the weak models could be thought as basic blocks to build the complicated models, and you will be able to, you are allowed to use existing implementation of those weak models. Okay, fine. Well, maybe let's start. I will share my screen. Yeah. Can you see my screen now?
Yes.
Good, good. Well, today we will study, today's plan is like that. We will learn, which I just said, new family of machine learning model, which is not simply one yet another family of model. We start from now. We start building complexity in the model families, and this family is based on what we have learned before. So, and secondly, we will discuss a little, not a little, we will discuss all what is needed for assignment 3. This one, and I have made the assignment available. Okay, so you should be able to read this assignment right now. If you are a student from 32513 and the assignment is not available to you, please let us know. Okay, so yeah, let us start. Oh, colorful. So as usual, we start with some review of our previous study, where we are. The big picture is we start from learning, discuss what is machine learning. We think machine learning is too good to be true goal of letting the machine to program itself and improve its performance upon some experience of performing some task. We call that software 2.0. And what is needed in this process are data, which is corresponding to the experience. You need to believe there is some trend to be learned, and the trend will exploit, will extend or generalize outside the data. And we do not have explicit mathematical functions. Therefore, we want the machine to program themselves rather than we program it. So then we discussed the 4 elements in this framework. Well, we discussed the framework, which contains 4 basic elements: the data, a hypothesis family. We have emphasized that the hypothesis family is a limiting factor. It's not like something that enables us. It is something that limits us. Limits us what? Limit us from imagining whatever relationship between the data that can be observed and the data to be the part of the data to be predicted. So we do not just allow any kind of relationship. We only allow some kind of relationship, and that is the hypothesis family. So there is a selector we call algorithm that helps us to find a particular member in the hypothesis family that best describes the relationship, and the selection is according to some laws. And in the 3rd and 4th session, we have discussed a particular family of data model corresponding to a particular hypothesis family, where we have adopted the very intuitive, straightforward method of considering one data attribute as one dimension of space, and give the hypothesis, give any data attribute a corresponding weight, and take the sum of take the weighted sum of the data samples. Well, then we will have a number. We have a linear combination of the data attributes. So this number corresponding to some gradient in the data space. And the decision will be made according to this number, which corresponding to cut a straight line or a flat hyperplane in the data space. And that is called linear model family. We considered a particular member of the particular category of the linear model family, which is the perception. We will review this a little bit later today, so I will not get into the details. The important part is we have developed a geometric point of view of processing data. We can consider the data as a vector, and the model parameter, which are the weights, also a vector. So the weighted sum corresponding to takes inner product of 2 vectors. And using this view, we have developed a learning algorithm for perception models. And in week 5 and week 6, we have considered decision trees, which corresponding to cut the data space in such a way that in each of the tests, we examine one particular data attributes, which corresponding to cut the data space along with all the other attributes. Cut it in this way, such as if we test x1, if the x1 is on the left-hand side or the right-hand side of this cutting point, and then we will split the data population in these two parts, and in each of the subpopulation, we can perform further tests. Okay, the test goes on and on until we have arrived at a situation that within each of the sub-region, the distribution of the y variable, the distribution of that is pure enough. So, which means the uncertainty of y in individual regions is low enough, so much so that we can reach some conclusion about this y variable. We have considered that first intuitively using if-else statements to directly program it. And then we have invented a data structure that can help us to formulate these if-else branches into, well, a tree structure where the information flows along the branches of the tree, and it will arrive at some leaf nodes where it's corresponding to the decisions. And we have considered how to construct such a tree using data. And the construction, the core computation in the construction is that we need to invent some measurement about the purity of variables. And then from here, that led us to studying the information theory, where we developed some principled mathematical tools to measure how mixed up or how pure a random variable is, which is entropy. Okay, you can understand entropy as some quantity that describes the mixture, the extent to which the contents has been mixed in a black box jar. Sorry, a black jar. Okay, and it's corresponding to, on average, if someone take random samples from the jar, and this someone needs to communicate to another, maybe girl, about the result. So on average, how many binary bits is needed to communicate such an event? So we'll have learned some information theory here. And in the 7th session, we took a review again. We have considered, okay, so all the learning framework we have discussed here, all the learning framework we have discussed here is based on some random samples that are taken from the data distribution. And then we realized that there is one largest uncertainty, one catasticity, one random factor in the entire learning process, which is the data distribution is actually a black box that is not available to us. The only information we have about this distribution is a set of samples. Okay. And given this sample, we have an algorithm helping us to find some particular member in the hypothesis family according to some laws. Okay, all these are fixed factors in learning. And we can see that this selected member differs in each round of learning, because in each of the round of learning, the input training data sample are different. And correspondingly, if we consider some particular X test, the prediction on the test sample is different in each round. And that difference is due to the variation in the random samples. Okay, so we have we established this randomness, and then we considered a particular quantity that could be evaluated from the results of learning, which is particularly useful. Which quantity? It is the error rate of a hypothesis, this quantity. And from the analysis above, we know that if we consider the quantity computed within the training samples, and we consider, so to emphasize that it's within the training sample, we will take this symbol here within some data sample. And we consider the difference of this within sample error rate and the true error rate. Okay, this difference is something that we do not like, because of the simple reason that this means the performance we have evaluated on the training samples is not reflecting the true performance level of the selected hypothesis H. So we want that to be a small thing, but that is not completely within our control. That is out of our control. So we can only discuss this in a stochastic framework. We consider a bad event. The bad event is the difference between what we have evaluated and what we care, but we cannot evaluate. The difference between them is greater than some tolerance, and this is a bad thing. And we can consider the probability of this bad thing. Why this bad thing happens with a probability? It's not certain. It happens sometimes. It happens. It does not happen at other times. Why? That is because this guy is random. So when the other things are fixed, the evaluation differs from time to time because the data sample are different, are randomly sampled from the population, and we have the theoretical bound. We have a theoretical limit of this quantity, which is very promising, because this quantity decreases exponentially with the number of samples. So that is Hofstad's inequality, which is our friend we needed. And then we consider a particular difficulty here, which is this guarantee is for some edge. If we are lucky, we get that edge, and we know that the evaluation for that edge is accurate. That is good. However, in the learning, our edge is not some edge. It's an edge that has been selected by the algorithm. So there is a possibility that by changing the edge for multiple times, eventually we arrive at some edge star, and unfortunately that data happens to be the bad data for the edge star. So this happens more often when the hypothesis set contains more hypotheses. When the number of the hypothesis set is rich, we are likely to get to the conclusion that maybe the training error is very good, but we have lost the guarantee of the generalization error. So, okay, basically, we have stopped here. Then that is the big picture of our journey. And today, our plan is back to the, okay, we talk about some theory, we talk about some model, we talk about some theory again, and today our plan is back to the model side, and to see that there are some very clever balance so that we can enrich the model family without catastrophically increase the complexity. So that is our goal of study today. We will study ensemble methods. Okay, so we will study high level. At high level, what? Well, where is that? I think I haven't made the note here. Anyway, at the high level, what are ensembles? And how to make ensembles, how to train ensembles, and slightly touch, ensembles realize the plan here to increase the capacity of the model while slowly increase or limits its complexity. So that is our plan. Well, let me find. Any questions? Are we okay? We have few people want to think a little bit more about that, and you can take the chance to ask me questions. And I think I can take the chance to share you the link of today's in-class notebook. It's just I think re-implementation of what we have done in the notebook on Canvas side. Well, however, I think I have just take the essential part and made it easier to understand. So yeah, in any event, let me copy the link. I've sent the link through the chat. If you would like, you can open the notebook and follow me in the following discussion. Okay, good. I think we are good to go. Well, ensemble methods. Actually, ensemble methods is basically an umbrella term. Well, you can intuitively understand that. Basically, I don't think you probably need someone to explain to you the basic idea of ensembles. It's quite simple. Give examples such as if you have Alice, Bob, and Charlie. Every one of them, they are like a member to make some decision, to make some judgment. You can consider them such as an admission committee. For example, they might want to enroll a promising student for like a PhD program or whatever. Anyway, they want to make yes or no decisions. Okay, and let's think about the possibility that they make good or poor decisions. Say, if they are of the same quality, each of them can make good decisions in 80% of the time and bad decisions in the rest for the remaining cases. Well, it does not it is not a huge surprise if I'm telling you that, well, each of them have the 80-20% of making good or bad decisions. Then if I made them a committee, this committee consists of A, B, C, and the committee runs according to some rules. For example, they can run with a very simple rule, such as we take the majority vote. For any case, we let A, B, and C vote yes, yes, no, stuff like that. Okay, and if they take the majority vote, well, I then think the chance that the committee made better decision is better. It performs more accurately than the individual members. So that is the idea of ensemble methods, basically put. Okay, so I don't think that is hugely counterintuitive and needs much interpretation. How do you think about that? Any questions about it? And I think a good way to persuade yourself and get a full understanding of what is what follows is try to work out all the situations those guys are making decisions and truly appreciate that the committee will work better. For example, as we have said, A, B, and C, they make good decisions in 80% of the time. So now let's consider the fact whether their decisions are good or poor. Okay, so we do not consider whether they have said yes or no. We actually consider whether the decisions are good or bad. Okay, so there is a possibility that every single one of them has made good decision. So that is good, good, and good. And what is the chance of that? Okay, that would be 0.8 times 0.8 times 0.8. So that would be 0.512. Okay. Well, then we can consider how about when Alice and Bob are making good decisions, but unfortunately Charlie has made bad decisions. So what is the chance of this? Then that would be 0.8 times 0.8 times 0.2, right? So that would be 0.128. Okay, and so on and so forth. Until you have the event that, okay, let's maybe do another one. How about this one? And so what is this? Hopefully I did not embarrass myself, whatever. I think maybe we have it. Okay, I'm right. That's good. So on and so forth, and you go all the way until you reach the exhausted all the possibilities. So then how can we make use of this? Okay, let's consider this situation, the good, good, good. And of course, the committee result will be a good one in this case, right? And how about that? Good, good, poor. Although Charlie has made a poor decision, but because Alice and Bob both made good decisions, so the committee will still make good decisions, right? Similarly, in this case, and however, unfortunately, in this case, only Alice has made good decisions, and the decision of the committee would be bad. So at the end of the day, if we sum up all the good decisions, the chances of good decisions and the chances of bad decisions, we add them together, we get 2 chances of the committee making good or bad decisions. Right? This would be better than any of individual member. So you can see from here, I make that maybe larger. So this is a only one member makes good decision. So the similar situation will happen when only Bob or only Charlie has made good decisions. So the total chance of the similar situation would be 0.032 times 3 and 0.9096. And there is another chance that all three committees has made bad decisions, and that would be 0.2 times 0.2 times 0.2, and that would be 0.008. So putting everything together, the chance of making bad decisions would be this and so it is only 10.4%, while the individual member will have 20% chance of making bad decisions. So that is the intuitive motivation for employing multiple predictors to let them to form a committee and taking vote. Are you with me now? So if you need, oh, where is that? Sorry. In the pool. Okay, I can relaunch the pool. So yeah. Okay, I think that is simple enough. Good. Let's continue. Well, this is of course the simplest possible, maybe the simplest system of getting the decision of a committee. Okay, but there is there is a very inconvenient fact here. Anyone want to raise a point? Can you ask a question? I would say, that is a good question. Well, you think about that. Where did us find Alice, Bob, and Charlie? Where can we find those three predictors and form this system in the first place? Why this is a problem at all is that there is a fundamental requirement in this for this system to work. Why? If we cannot achieve that completely, we want the extent to be as much as possible. What? We want all those predictors are as much independent as possible, as independent as possible. So consider a counterexample. Maybe, unfortunately, see Bomb, he does not have an independent mind. Bomb follows whatever Alice votes for each single decision making. What happens in this case? Simple. In this case, Alice will be the boss, and Alice will dominate the committee. And unsurprisingly, the performance of the committee will drop to the level where Alice is. And then there is no point to form such a committee, and everything Charlie has done is wasted. And Bob hasn't done anything at all. Don't think that is a simple thing. It is not very, it is quite easy to get weak predictors for practical problem, but it is entirely another story to ensure that our candidates to our members of the committee are independent one from another. Okay, so there has been proposed quite a number of different methods to help build a system that keeps the weak classifiers independent while they can work together to form a committee. Okay. And in the introduction to data analytics subjects, some of you have already been exposed to some of the ensemble methods. Today we will focus on one of them, which has been used widely, and especially if you are interested in such as data scientist positions in the industry, that would be very helpful, because the classifier we will introduce is suitable for a wide variety of data type. Okay. So the algorithm we will discuss is AdaBoost today. I'll show you here. So it solves the problem of forming different independent weak classifiers by adopting a clever design. How to make the weak classifiers independent, different? Well, how about if we train the weak classifiers using different data samples? Well, that plan will immediately lead to another difficulty, and the difficulty is where it comes the different data samples. In theory, we are very happy, such as we can analyze the behavior of an algorithm. We usually call that behavior asymptotic behavior. Okay. So asymptotic. Okay, my spelling asymptotic, which means if you take the number of samples to infinitely many, or you train that for infinitely many times. However, unfortunately, in reality, you have data, you have the data distribution, and which gives you some data samples, and that's all. You only have this, and this is the only source of information you get. And how from this to get multiple hypotheses. Okay, the clever design works like that. Instead of using this guy, we resample a data sample from that guy that is data copy 1, and using data copy 1 to train a hypothesis, and use data copy 2 to train the hypothesis, so on and so forth, like this. Okay. And secondly, we want to let the committee vote, and in either vote, each committee member does not act equally. And that is a very clever design. The committee members are organized in such a way. If one predictor has performed well in the training, it will be given a higher weight. It will associate with a weight. Okay. If it performs well, the weight will large. If it performs badly, the weight will small. So at the end of the day, when you put them together, and the committee will, when the committee is going to make a decision, the decision making is according to those individual weights. Okay, well, and more clever. So, well, I think I should put one separator here. Think about that. When I'm at a point, I have employed a weak classifier or a predictor, a base predictor. Sometimes I just use different names of that because they have different names in the literature. So when I have some member prepared and I have created a weight for it, and I want to employ the next one, how? Well, as we said before, we retake a random sample from our data sample and use this retaken sample to train this guy. But what I'm going to do is even clever. I will consider, okay, I will consider the performance of the previous hypothesis on all the data samples. So maybe this is correct, this is correct, this is incorrect, this is correct, so on and so forth. Okay, and when I resample the data into its copies, those ones that has been successfully predicted will receive less weights. They will be underrepresented in the new copy, and those who has been misclassified, where the previous hypothesis, where the previous weak predictor has made errors, will be overrepresented in the new sample. Okay, it will have more chance to to join this new copy of samples, I have to remind you that the copy of samples can have repeated data points. So maybe if this has been misclassified, it could be sampled twice in the new sample, which means when training the new hypothesis, the new hypothesis will be really focused on those overrepresented samples, because if it made bad decisions on those overrepresented samples, those errors will be counted repeatedly. Okay, so that is the idea. And have I made the general idea clear? And if you are happy with me, with what we are, if we are on the same page, I think we will get into the details. Or if you need some more explanation, let me know. I have several people want more time. You can speak up. Okay, anyway, let's get into the code. Sometimes it's when things has some room for misinterpretation, and that room will disappear when it comes to a computer program. Okay, so let's get into the code. First, let's have a look at the data. In this week, we will start considering slowly, considering some more interesting data. So for the first time, we say bye-bye to our good friend, Iris. What data we will consider is these guys. Okay. This data set is also from the scikit-learn data sets. These are handwritten digits images that you have often encountered when people start introducing deep learning models. So we can take images of people's handwriting, and each image can be considered as a data sample. It's no, there's not much difference between such data sample and our old friend Iris. Just consider one image as so our image has 8 by 8, which is very, very small. Okay, our image has 8 by 8 pixels. Okay, well, the image of handwritten digits is represented by the values of these 64 numbers. So let's consider where the ink is of a high value and where the blank space of low value space. Okay, so maybe here will be an attribute of 0. We call that x0, and here x1 also 0, and here 0. Okay, you go all the way until you reach here, maybe. What is that? 7, 8, 9, 10, 11. So you go all the way here, you have x11. okay? And this might be 0.5 because my stroke does not take the whole pixel, so on and so forth, until you have X 63, which correspond to the last pixel here. So basically, an image is not very much different from a flower, okay? And the task is, well, less intuitive, but still understandable, is to decide the identity of this image. By identity, we mean 1, 2, 3, 4, 5, so on and so forth, according to these 64 numbers. Okay. Well, obviously, this task is much less intuitive to solve than the Iris flower example, because you do not have the nice visualization of those data points in 64 dimensional space. Look, if we consider such as a perception type of model that will consist of 1 dimension, maybe 2 dimension, maybe 3 dimension. Okay, and from here on, we as a 3-dimensional creature is less able to imagine, but you can use your mathematical mind to appreciate that each one single dot of this guy, point of these guys, is living in the 64-dimension space. And our task is to manipulate, to create some boundary in the 64-dimensional space to classify those digits class. And as usual, I have simplified the 10-way classification problem into 2-way classification problem by letting us only consider the numbers of 1 and 5. Okay. So our data is in such a way. If it is, let me have a look. Yeah, if it is 5, then we want to label it as negative. If it is 1, we want to label it as positive. It's I hope the data and the task is clear enough. Are we okay to go? Okay, beautiful. Okay, so well, it's I have to admit it's a quite counterintuitive, quite abstract to imagine some mathematical formula to handle such data. So how about let us first maybe reshape the data attributes back into 8x8 arrays. So what I'm doing here is look, the training sample consists of 273 samples, and each sample contains 64 attributes. And what I'm doing here is just to take the first training sample and reshape the numbers in a way that I can, well, better understood. I show you. So if you take the first training sample, it in such a way, although it looks like be organized, but actually it is not. It's just an artifact of the printing. Look at the bracket here. It has only one bracket. If I think if I'm dragging my my screen in such a way and reprint it, it will be much less. Okay, sorry about that, but you get my point. You do not actually has any structure of this. However, if you reshape it into 8 by 8, notice that I have a parenthesis inside the reshape. So the reshape takes one parameter, and the parameter is a tuple. Okay, so yeah, look now. Now the data has been organized in such a way that it knows rows and columns. This pair of brackets represent one line in the image, and this is the second line, so on and so forth. So with this organization, let me invent some weak classifiers. Note, it's really weak. What I'm going to do, I will take my intuition. I will consider. So let's consider the image in such a way. I will take everything on the left-hand side and subtract everything on the right-hand side. Okay, I will take the sum of all the brightness on this side and take the sum of the brightness on this side. So this will end up with a number, for example, 8. This will end up with a number, for example, 7. I will subtract it. What I mean is I will take the left-right contrast of the image, and I will use this contrast to classify whether the image is positive or negative. So to a computer code, that would look like let me make X0 to be this. Reshape 8 to 8. Okay, so that will make things look clear. What I'm doing is to take the sum of that left-hand side. So this means everything, every single row, but only to take the first 4 columns. Let's have a look what we have here. Okay, 1, 2, 3, 4. We take the sum of it, this number. Okay, and I can subtract the from this sum of everything from 4 to 8. This. Okay, then I will see. I would say, okay, on this image, the left-hand side is slightly brighter than the right-hand side. Okay, I hope this can distinguish 5 and 1 a little bit, but this is only my intuition. And the intuition might work or it might not work, I don't know. For example, when you write 5, it seems that the 5 is, well, less symmetric than if you write maybe 1. But I don't know. Let us see. Let us see. Okay. So where is my? Okay. Okay, I will create a way of computing this more systematically. how would I do this? I will do a mask. I call that M1 to be okay, so you can see C map means color map because all the colors are artificially assigned. So I like it to be black and white. It is like this way. On this side, I will use the okay. I will contrast this part and this part, and the black part will be the negative part, and the white part will be the positive part. And how can I compute that? I would just take the element-wise multiplication. I will times for each element. I will use M1 times 0 and use this to subtract 1 minus M1. 1 minus M1 will flip the side of M1 times X0. Okay, look at the result. It will be the same. Why I'm taking this approach? That is because remember the Alice Bomb Charlie example? Okay, so what I'm going to do is, well, I will implement several of those classes, the weak classifier candidates. Well, when I'm just changing the mask here, I will end up with different contrast making methods. For example, if I'm taking this, I will contrast the upper side and the lower side. Okay, so if I'm taking the contrast of this, I will consider a chessboard pattern. So anyway, here is a demonstration of different templates I'm going to use. Okay. And a classifier is just to well, compare the contrasted regions of an image and see if which part is brighter, and if the brighter, well, and according to that make a decision of whether this is a positive or this is negative. This is a classifier. How to train that? Easy. We apply this classifier to the training image, and because this is a two-way classification problem, there is only well, you have to be, or very likely you will be end up with one of the two situations. Your prediction is better than 50%. Alternatively, your prediction is worse than 50%. Okay, if your prediction is worse than 50%, what can you do? Well, you just flip your prediction. So previously, you thought, okay, if I take this part and take this part and take the contrast, if the contrast is positive, I will say the sample belongs to class 5. Otherwise, this belongs to class 1. And if you happen to find this strategy is so bad, it's the accuracy is less than 50%, you can just say, okay, I can just flip my decision. When the contrast is positive, I will consider that to be maybe a class which 1 or 5. I didn't remember what I told you. I said before, but you get the point. Okay, so that is the basic idea here. Okay, now we have candidates of weak classifiers. And what we are going to do now is one key step of the ensemble. Where is that? We will resample the samples into new new population, new samples. To do that, we will need to assign a weight to each of sample. So what can we do is I'm showing you step by step. This will give us a random sample, maybe from 1 to 3. Okay. Sorry, 0, 1, 2, 0, 1, 2. And we can ask the function to give us multiple samples. Like we take the sample 10 times. How about that? Okay. Okay. And we can tell the different possibilities of taking each of the candidates. For example, then the vast majority of samples will be 2. Okay, if you sample 100 times, maybe you can have 1 or 2 things that is other than 2. Okay. So you will have very rare 0, some 1, many 2. Okay, what we are doing now is we have 273 samples. Remember that? Okay, what we are doing is just to take 273 samples from 273 samples. That is what we call to make a copy of the training samples. Okay, not very surprising. And in the initial step, all samples are equal. So the sampling probability will just be like that. 1 over 273, 1 over 273, You have 273 entries of this. This is the probability. Okay. So yes, we move this. Okay, after we have taken the resampling, this is just to extract the in the first resample we take the index, we resample the index, and in the second and next we just take the sampled x and y parts from this index, which is trivial. I will not repeat here. Okay. And what we are going to do here is, say for example, consider the T1 classifier, which is this one. Okay, we consider this, and we use this to as the contrast, and then we do the prediction according to this contrast. Okay, so for example, look, now we have xi as the resampled sample. So xi sheep, you can see it has 270. Where? I have to run this. Sorry about that. So it has 273, and we take the first one of that. This is one sample, and we can use contrast. Classifier. Am I typed that rightly? Yes. Okay, we classify this using T1.
You have an extra S in contrast.
Thank you. Okay. So it returns 1. So that is a prediction of the first resampled sample using the first weak classifier. Well, we can do this in such a manner. Okay, I didn't change anything seriously. Not interesting at all. Okay, however, I can do this for x in here. Okay, then I give it a pair of brackets. I will get the prediction. All the 273 predictions. Okay. So let me remove this. This is basically what's happening here. This is a prediction, and well, then this will be whether the prediction is the same as the desired value. Okay, we can show you maybe. This will be the prediction, and this will be the desired value. So they are the same. If they are the same, I have one accurate prediction. So if we do this for everything in the resampled data set, we will get the accuracy of this making prediction use this particular template. which is very simple. And here is the judgment. If we happen to be very unlucky that the prediction accuracy is less than 0.5, here is greater than 0.5. There's not much interesting thing happens here. If it is less than 0.5, we what is 1s? Okay, we will make we will remark this, that the prediction of this contrast classifier needs to be flipped, and the accuracy, we do not need to recompute the accuracy, because it's simply just where it is wrong, it becomes right. Where it is right, it becomes wrong. So the accuracy will just be 1 minus the accuracy. So that is the training of weak classifier on the resampled sample. So that completes the sorry, that completes this step. So, and in the next, I just summarize whatever that has been done in a for loop and put that in a function. And in this function, it will select one best template for this round. Okay, so that does not matter too much. I just not very interesting. It's just some bookkeeping steps. So this is the repeated steps. Put the above step together, and in the first step, the best template happens to be this guy, the guy we are familiar with, and this computation is important. We will compute a weight for this classifier according to this. That will be this. Okay, I think this is best understood using an example, using some examples of the particular numbers I show you. Okay, let's consider the error rates. Say temp a. Okay, I start from 0.01 to 0.991, and with a step of 0.01. So you can see what I'm going to investigate is I want to consider the weights received by classifiers that has achieved the performance, the accuracy of 0.01. Sorry, the error rate of 0.01 until very, very bad one. So actually, I do not need this one. Later, I will show you. So the temp alpha will be numpy a range. Sorry, no. Numpy dot log 1 minus temp c. So we need another pair of parentheses here. Okay. See, let me make it more clear. What does that mean? When the error rate is very small, that classifier will be given a high weight. When the error rate gets worse and worse and worse and worse, this classifier will be weighted less and less and less. Okay, actually, we do not need the part here. We can just stop at 0.5. Why? Because when you consider a two-way classification problem and your accuracy is less than 50%, remember what we have done before? We just flip it. So this is the actual range of error rate we are considering. The less error a classifier is made, the higher accuracy, the higher weight it will receive in the committee. Okay, when it is so bad that does not differ from the random guess too much, so it share a very, very minimal voice in the committee. Okay, so that is what does it mean here. This is just for numerical stability. In case, for example, if you happen to achieve 100% accuracy, you do not receive infinite weight. Okay, but that doesn't change the logic of our discussion too much. Okay, now we have trained a weak classifier. We have given the weak classifier a weight. And in the next, basically, one step has been done here. So what happened next? Next round. However, before we do the next round, we will want to adjust the weights of the data samples. We want the data sample that is wrongly classified by the current classifier receive a higher weight, and those that have been correctly classified will disappear from the next round of training because we do not need that information. And that makes much sense. Consider a more intuitive situation. I return to our old friend, Flowers. For the sole reason that I am not able to draw a 64 dimension space, consider a two-dimensional space. Okay, if we consider this two-dimensional space and our maybe positive, negative samples are here. Okay, if I'm letting you to draw a classification boundary, you probably drawn it somewhere here. For this boundary to work, well, you will see this guy, this guy, this guy, this guy, this guy, this guy. These guys contributes most to define where the boundary is. They are the soldiers of the two groups of samples. They are in the front line. They push back each other. They do not let the population mix up. So you get the point? Well, and this kind of thought reappears in machine learning from time to time. I hope this picture somehow remind you the previous study, not in just this subject, the introductory to data analytics subject. You have been introduced a model called support vector machines. With that picture, remind you something about that model, well, I let you to check that back home. Okay. In any case, what we are going to do is we will adjust the data weights according to whether it is correct or incorrect to classify the particular data using the previous weak classifier. So now the data weights are this way. And the classifier comes maybe wrong, right, wrong. And what do we want? We want then this will be this way, this will be this. Okay. So in the next step, when you put the weights, this kind of weights into, remember the weights of sampling, those wrongly classified one will have more chance to appear in the next round, and it has a chance to be here to define the classification boundary. And more than this. So look, now we have a factor of well, expanding or shrinking the chance of appearance in the next round. But how much is this factor? It turns out in this design, the factor is linked to the weight of this particular classifier. So that makes sense. If at some particular sample, a very capable, a very able, a very accurate classifier has made mistakes. So that means this sample is a really, really difficult to classify. We will need really to increase its chance to be overrepresented in the next round. On the other hand, if, for example, a classifier that is not very much better than random guess, then the performance of such a classifier will not say too much about how difficult a sample to classify. So to summarize, what we will do is we will enlarge or shrink the chance of one sample to appear in the next time. Look, this time we will evaluate on each sample on the original training sample. We will evaluate here, not the previous copy, okay? We will evaluate on X train, not Xi. So we evaluate this. Maybe I can copy this out to show you. So this actually is not a very good name. It should be called error. It's to direction to adjust. So that is a more accurate but too lengthy a name of the variable. Direction to adjust weight. then you will find this. Okay, correction to adjust. Let's consider the first 10. This is to shrink, to shrink, to shrink, to enlarge. So let's investigate. So X train, the first one, and compare that to Y train, the first one. This should be the same. Therefore, this sample, the first one, will receive less weight in the next round, right? Oh, sorry. I forgot this SI. SI would be the flip or not flip, because I think in this case we flip the classification. Okay, this will be the same one, and in the consider the next one should also be the same. This guy. So the classification is also right. And let's consider maybe this one. 0, 1, 2, 3. The third one. The third one. Okay, they are not the same. Maybe we can also have a look at the first one. Okay, the first one is the same as well. Consider the third one. Right? So maybe we can also consider the TI. Basically, what does it mean is if we use this template to compare the contrast of okay, the white part and the black part, well, when we apply some rule to classify this 5 as 5, if we apply the same rule of classify this 5 as 5, when that rule applied to this one is also classified as 5. So probably we consider if this is brighter than this, it will be 5. Maybe if we apply the same, this one is misclassified as 5. So that is what happened. And therefore, in the next round, this sample 1 will more likely to appear. And when we choose the next classifier, the next classifier need to put more emphasis on this training sample. So that is the logic. Okay. Well, when we have this direction, and when we multiply that with this alpha I. Do I have an alpha I? Sorry about that. So okay, it's called alpha I. Okay, the factor is in this way. Okay, and we take the exponential of that. Okay. After we have shrink or expand the chance of samples to appear, we need to well normalize that into make them to sum to one. Okay. And next, I just put together everything, and that makes the AdaBoost classification. I have to admit that this is not the well, that's not. It's very easy to understand, but does not show the full strength of that. For one thing, the weak classifier class here is too weak. Okay, but anyway, you can see starting from a very humble start, we only have maybe at most less than 70% of the accuracy. We can reach, I think, later more or less approximately 80%. If we use a slightly stronger weak classifier, such as using decision trees, but using decision trees with only one level, that means we are allowed to employ weak classifier that judge one pixel, only one pixel, and we combine those pixel classifiers together. Here you can see that the weak classifier is to make a decision tree with the depth of 1. Okay, so if you do this, it quickly gets better. I think I'm sorry. We get slightly over time. I don't have enough time to get a very detailed discussion of assignment 3. But I will stay here for a little bit longer. I will point you to the specifications. Okay. So yeah, let us go to the quiz first. Where is that? Sorry for that. I think I spent a little bit lengthier time to explain the models. Okay, our quiz. But fortunately, the quiz are very easy today. So the first one is exactly the example we have discussed in class. You have 3 members, and these 3 members are independent and have a 20% of chance of making errors. So when you put them together, let them vote, the chance of making errors is only 10%.
Sorry, Jun, you haven't made the quiz available yet for us.
Really?
Yeah. For quiz 8, right?
Yeah.
It says the quiz is part of an unpublished module and is not available yet.
It's is that for everybody? Everybody, if you have a
Yeah, for me.
Let me have a look at that.
For me too. Says the same thing. It's not published, it says.
I think you forgot to publish the whole module for week 8.
for week 8. Let me have a look.
There is no pre-reading for this week.
It's not published, June.
Yeah.
Oh dear, no, because everything here is published. This is my apology. Sorry about that. Okay. I thought everything here have already been published. That is unfortunate.
Yeah, we can see the quiz now.
Sorry about that. Okay. Hopefully that won't make it very, very difficult to study here. Anyway, so let's have a look at the quiz. I was scared. That is Okay. The first one is just what we have discussed. It's 10%, 10.4%. And the second one is it's discussing the very simple ensemble system we discussed in the beginning. That is to train the classifiers using just a simple resampling of the training samples. Okay, so I'm as usual, those wrong answers remind us some take-home points here. So the first one on my screen is wrong. Why? To train the base classifiers, training data sets are randomly resampled from the original data set right up until here, all right, but the classifiers are independent. This is wrong because those resampled samples, although our best hope is that they are independent, but they are from the same training data set. So eventually they are linked, they are not independent. We don't have this ideal situation in reality. We observe an independent training data set to learn individual base classifiers. Wrong, we don't. This is a luxury we hope, but we do not have. The ensemble classifier is more accurate than any of the base classifier. This is not guaranteed. This is a hope. When we learn the base classifiers, the training data samples are resampled. Basically, this is the same as the previous one. Therefore, the sole learned classifiers are not independent. This is correct. So the correct answer is the training data sets are resampled and the classifiers are not independent. So question 3 is just to remind us some common misunderstanding. Resample is a resample without with replacement, which means we can resample the same data points, the same data sample multiple times. It is a desired feature. It's not a bug, and it is meant to be, for example, appear twice, 3 times if we need it to be overrepresented. So repetition is expected and valid. Okay. 10.4, resampled, not independent. Repetition are expected. Okay, yeah. Well, I'm talking a little bit about assignment 3. We have only 5 minutes left, but I can let me show you the let me just show you the most important part. So we are 32513. Okay, and this is an easier part. Good. So the task is basically based on what you have, what you are doing in assignment 2. So you are going to make a short video presentation about your implementation. We only have a maximum time limit. So you have to limit the presentation in 5 minutes. In the 5 minutes, you are required to address those points. Okay. First, what is the algorithm, it process what kind of data and produce what kind of outputs. And to do that, the algorithm, the learning algorithm consists of what kind of elements. Two, how to train the algorithm. Sorry, how to train the model. What is the training algorithm? Such as if you are doing decision trees, you can say, okay, here is my decision tree builder. At each node, it needs to select one particular data attribute to perform tests. And according to that test, it will decide whether to return a decision or to perform further tests using other nodes. And if further test is needed, here is a recursive construction of the tree structure, so on and so forth. Okay, and you will need to talk about some experiment design. Okay, here is my data. I split data into two parts, and the training data are given to my algorithm here, where the output is like this. Therefore, I have a confidence that my learning algorithm is working because look, the loss function, the criteria gets improved during the training process. And after that, I have test my algorithm using this, maybe this part of the test data. And here is the performance. The performance of the test data is comparable to the training data, therefore it's valid, or whatever. Maybe you have bugs or have issues, you can talk about that. It's okay. Such as, okay, the performance on test is less than ideal, probably because maybe I do not have enough data, I have this and that issue, that are all okay. You are expected to discuss some of the issues in your implementation. Okay. So, yeah. That is for assignment 3. I think I have, maybe I haven't, let me have see if I have set up the due date right. No, I haven't set the due date right, but the due date is in the subject outline. I will set the due date according to the subject outline. Okay. Wow. 1 minute before the end of the session, I finished. Okay, I still be here for a while. Any questions?
Sir, I have a question. So in Ensemble, we weight both the classifiers and data samples. So the classifier with the highest weight will dominate the comedy, right?
Oh, no.
Oh.
The classifiers will be weighted differently. Let's have a look. Say here I have put all the trend weight classifiers in this capital H. So, oh, by the way, I have a slight note about neural networks, which can help the study in the next week in this notebook. You can forgo this part, but if you are interested, you can have a look as well. Doesn't matter. Okay. So let's have a look at the H. Okay. See, H consists of many weight classifiers.
Yeah.
So it consists of 10 of weight classifiers. And I have append the weight here. So the 10 weight what? Sorry, should be here. So 10 weight classifiers has weights of this Look, even this guy, this is the strongest one, I think, maybe 1.1.2, okay? This one is the strongest one among those weak classifiers, but it does not dominate the classification. If, for example, the following two disagrees with it, the following two can overthrow its decision.
I see. But for the data samples with high weight, they have more chance to reappear in the next sampling.
Yes, 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 yes.
Oh, I see. But I have another question. It's kind of dumb, but why do we call the classifiers weak classifiers in the first place? Is it because they are better?
That is a really, really good question. I didn't, because it happens because the thing in machine learning can get really quickly hairy. So remember our discussion here. In the previous discussion, we consider this, and if you remember, we have discussed that when the family of the hypotheses is rich, is complex, is strong, is capable, the number it contains increases. And in such case, the guarantee the learned result enjoys will decrease. So basically, you have some complexity measures how rich, how capable of this capital H. This capital H is not that capital H in my code, not the same. This is means the family of the classifiers. Please understand that. When this increases, the penalty factor in front of this guarantee will increase. Okay, we will have weak guarantee of the validity of the learned model. That's the basic theme here. And why people would happily employ weak classifiers rather than build the complex, more capable ones from scratch. Because usually the weak classifiers, they are weak in the sense that the corresponding capital H family is smaller. It's smaller, and the guarantee here is better. And by constructing the stronger classifiers using those basic weak ones, theoretically, we can inherit some advantage enjoyed by these weak classifiers. Because the selection, the out of our control selection part is mainly in the training of the weak classifiers. So the bound enjoyed by the weak classifiers could be combined to contribute to a bound of the final stronger ensemble classifiers. So if you want to, this is inherently less discussed. So this is a paper which is by one of the founding fathers of this family of models. You can take a look at that. It's called A Brief Introduction to Boosting by Robert. So here is the algorithm we introduced today. Okay, well, the lengthier discussion I'm putting here, so you can take a note if necessary. Okay, it's here. In this paper is from 2002, almost 20 years ago. Ah, well, time. This paper was new when I was doing when I was doing my PhD. So look down. In this paper, it discusses if we combine those weak classifiers into some family of capable or more richer classifiers, the rich one will inherit the bound of the weak classifiers. I remember it is in chapter section 4. If you're really interested in this, you can look at chapter 3. This theorem. I think I'd better not discuss this in this class, but
Yeah.
that is basically what is going on behind the scene. Okay, so you can take a note of the name of the paper. It's really really precious piece of the intellectual achievement.
Hi, Jun.
Hi.
Can I ask you a question about the ID3 algorithm?
Yeah, okay.
Yeah, so the code I'm looking at is, I think it's in a week 6 module.
Yeah.
And it's the US election analytics.
Oh, you look at that one. Okay, I can let
Yeah.
you share your screen if that makes
Okay,
it easier.
sure.
Yeah.
Yeah, can you see my screen?
Yes. It was a hot topic because I made that in 2020 last year, and I analyzed the data from 2016. Okay.
Okay. Yeah, because I've found this one is quite suitable for my assignment too. So I'm trying to refer to this code for my assignment too. And the part I don't quite understand is in the predict function here.
Mm-hmm.
So this one only have like these 2 simple lines. What I don't understand is how it actually work in the background to like do the prediction progress.
Oh, can you make the font size a little bit larger? It's slightly difficult to point to. Okay, so what it's doing here is look, we only consider this branch because this branch means you have already reached the leaf of a tree and you just return the result.
Yeah.
Okay, so this branch means now you are in the internal. I'm not sure if I am using a binary tree. Maybe not a binary tree.
It's I think you used like
whatever
quartile.
tree.
Yeah.
Yeah, it's not a binary tree, whatever tree. So here means you are inside a tree and you're looking at some internal nodes. And so the task is to decide which way to go, right?
Yeah.
And to decide which way to go, we find an attribute to test, which has been determined in the training stage. Because look, although this happens before this, but in reality, this will be executed always after this.
Yeah, the fit method, right?
Yeah, you first run fit and then the predict.
Yeah.
By the time this is running, you already have this guy
Yeah.
So this will be which data feature to inspect. In this case, it would be like I do not remember, like education years or the
Yeah.
age.
The column names, right? The
Yeah,
column
yeah,
name
stuff
for the
like that.
dataset.
Yeah, yeah.
Yeah.
And because we are going to do prediction for a particular sample, which means, okay, this is the F table and this is the sample, okay? And here, this guy will point you to a particular element in the sample, and here it takes the value of the sample, okay? When it takes out the value, attribute value, I think I have quantified the value into maybe 0, 1, 2, 3, or the value.
It's Q1, Q2, Q3, Q4.
Okay. So the value is one of the Q1, Q2, Q3, Q4 one. So the children will be pointed to by that value. So the Q1 will point to this children, Q2 will point to this children, this child, so on and so forth. Okay, so and after doing that, what you are going to do, you just dedicate the job to the particular key child. Okay, and then the control flow will be here. And then here, the predict will call itself here. And now you will either decide whether to return, or when you go to this branch, you will get into another children's children. And then you go back, and then you go back until you reach the end of sorry, the one of the leaf nodes.
Okay. Yeah. So the child dot predict is actually is gonna do the iteration again.
Yes, it's exactly this one. Child dot predict means predict, and this self will be just as this child. And this sample will just be this sample. So basically it reads like, use this child to do predict.
So the children here is like a dictionary of a combination of like child tree nodes, which is different from the tree node of the data set at the beginning.
Okay, the tree node has the tree node has a data set only when it is at the training stage. After training, it does not have a data set. The data and the tree node, they are linked but not the same kind of concept. A tree node represents a region of the data space. When at training, that space is specified, is represented by a set of samples from the space. And at test, the samples has been removed, no samples left. Only the space is there. Okay, well, consider it is, how to see, maybe like say if you are there dust to some some region of a board, and maybe it has been revealed to you. Here you will get +6. Here you get +5 points. Here you get -3. Here you get -2. Okay, and you then learn that the distribution of the scores on the board. And after the learning, you have maybe have a way of distribute your shots. For example, if you are after high score, you will maybe want to shoot this region, and that has been learned. After this has been learned, the previous samples are not required. You do not have to keep the previous samples.
Yeah, I understand this part. I think what I'm confused of is about this this children and child part, that I'm not sure what they are actually referring to. Are they referring to for just this single column, this split feature name?
No,
are.
This is the when this like attributes name.
Yeah.
This refers to the data. However, these guys are of a tree. Okay.
Yeah.
These guys are the children of this guy.
Yeah.
These guys are the children of this guy. And well, this is a node. It needs to have some way to organize these guys. So it will have like a children structure, and the children structure consists of 4 elements. So Q1 will be this guy, and Q2 will be this guy. This is the data structure. When it is it is put in use. Okay, when this one is processing some data sample, say if this is given to this one,
yeah,
it has also another attribute called split feature name.
Yeah.
Okay, so the split feature name will take one particular sample, one particular value from this data sample here. You use this to find a value here, okay? And this value will be Q1 to Q4, one of the Q1 to Q4, okay? And
yeah,
according to which value it is, you will call one of the children to further process this particular data. If, for example, here is Q3,
yeah,
this one is Q3, okay? And then you will call your third children here, okay? Then this guy will process this and using exactly the same procedure.
So it will process still in this row.
Still in this row. Actually, it does not know any other rows. There is no other rows. There is only one.
Yeah, okay. So so the first one being processed is the attribute with the most information gain. And if it move on to the subchild, it will move on to the attribute with the second most information gain. Is that
Mm,
how it works?
no. The information gain is when we talk about information gain, we talk about a population. For this single sample, for this guy, this one, it does not have any information gain. No,
Okay.
this is the predict stage. The information gain is used to fit. These are not the same same procedure.
Okay. Hmm. I will take a close look at it.
Okay.
Thank you. Yeah.
Hi, Jim. I had a question about decision tree implementation as well. So for my training data set, there are some of them, like not all the queries are covered in it. So my test data set kind of has these extra queries. So when I kind of run like predict on my test data set, it causes errors.
Yeah, exactly.
Yeah. So what would you suggest us to do in this case? Like, should we train the model on the entire data set? Because I mean, that's not something that we should do normally, but like in this case, when there's extra queries in the test data set, what would we do?
It's very much depends on your business task. It seems that you are touching some very interesting points here. Are you using some practical data?
I'm using a data set from UCI.
Okay, good. That is basically a good thing. It's you touch a point that we haven't touched while learning. We are in an engineering world, so things always get more interesting when you touch practical data. Well, if you ask me, you are the one who are working with data. You probably be able to come up with more reasonable solution than me. But if you ask me, I would simply say maybe just throw away the attribute in the test. Why? Why throw it away? Because that piece of information happens to be unfortunate enough to appear while we are learning the model. Because we haven't encountered at all that attribute while learning the model.
Then, like the attribute you're seeing it, but mainly like that particular query, like as in, for example, like the attributes are there, the values are there.
Like the value, for example, say if we consider the gender of people in your training data, you have male, female, but somehow you end up with a population with transgender people. Then
no, that's not the case either. So the case is like the values of the attributes are also the same. It's just that, for example, you have a tree. So if you build a tree on your training set, okay, I'm not sure how I can show this, but would it be possible for me to like draw on a whiteboard or something?
Yeah, if you on your Zoom.
Yeah, I'll just do that then. Are you able to see my whiteboard?
Yes, I can.
Okay, I'm not sure how well I can explain this, so yeah, I'll try. So if I'm building a tree on my training data set, I might have, for example, I'm splitting on weather, okay? And on my training data set, I'm splitting on weather, and I split on weather, and then later I split on some other attribute. For example, I don't know, maybe some colors, okay, like green and blue, okay? But colors originally have green, blue, and red, okay? So over here, okay, let's see. Yeah, over here, we're splitting on some other attribute and we're again splitting over here. Okay, wait, I'll write it over here. This is splitting on color. This is splitting on color again. Over here, we're looking at all three values, okay, red, blue, and green. But over here, we're only looking at red and blue. But in my test data set, I have a sample which requires it to go. So imagine this is sunny, okay? And this is red and blue. In my test data set, there's a sample that has weather as sunny and then color as green. So it hasn't seen that particular query.
I mean, yeah. I understand. Which means that similar to the situation I was discussing. However, now the same set of values appear both in the test and the training data set. However, it does not appear in each subsample of the training data set. Therefore, in some of the nodes, that node only see partially all the possible values. Right? Yeah. One solution could be we can start with all the unique values in the data set. So which means we can also build a node of the green here. However,
so that would be like
empty.
When you're training, you'll be like splitting on the
red
original sample, like the training samples split, right? Like attribute values.
You split the subsample, but the split criteria can be according to the unique values.
Yeah.
Such as which means in some subset you get an empty.
population.
And I think if you have a look at our implementation, you will find we have already considered this. We have a branch of the in the fit. I think in the fit method, we have considered that if the length of the y value is 0, which means if you get into this and you consider the subsample taking the color value to be green, and that subsample has nothing. So the length of the y value of subsample is also nothing. And in this case, you can return a default decision. And I think this has been considered in the original implementation in the notebook.
I tried it with the original implementation. It didn't seem to work because mainly because the split wasn't there, right? So I tried it with the notebook that you.
I know. What I mean is the zero length population is included. You can deal with the zero length population, but you still need to add the possibility.
Split, yes. I found this other way of like when I was going through it. I thought of everything disappeared. Okay.
Sorry about that. I need to. Sometimes I always do this. Okay.
So what was I saying? So what I did was I trained different models. So in my decision tree implementation, I also have hyperparameters. So I did all of that. I trained different models and then chose a model after testing it. So what I did was I tested it in the loop itself and then chose the model if it doesn't show any errors. So like, for example, I have in the loop, I have hyperparameters, right? Like depth or like minimum samples. So some values, when you set some values to those hyperparameters, the model won't cause any error when you predict the test data set thing. So I'm not sure if I'm explaining all right, but what I mean.
You explained it right. Yes.
So is that allowed? I'm not sure. Like.
No. It's a very good. I think you put both the previous issue and the current question into a discussion. It's very, I think, spot on. It's good, very good. And I I need to show you the hairy part again. Shorter story, you split the data not in two, in three. This is for
you want a test validation and training set?
Yeah, this is for validation.
But the thing is, again, what if in my test set there's a sample that doesn't consider? Like, then I'll have to manually like look through the samples and like see which one.
Okay, I understand what you mean. But in that case, the technical issue you can deal with in whatever way. You can maybe just look at the entire data set and put every possible values here. It's okay. But
okay.
Yeah, but split into three is
better.
The standard practice in industry. Yeah, so the lengthier explanation is, if you remember the Hofstad's inequality, that is E in, E out, this bad thing happens is smaller than something, and that is a very good one, but it's not applicable because it applies to a particular edge. So when it's a training, that edge is from some capital H, and the entire possibility of the possible edge need to be multiplied here, which blows up the tolerated chance of making bad things happen. Well, one remedy is that hide carefully the part of the data from training, and don't care about that at all in training. After training, you have some H star, okay, and test that H star in an in H star D test. So because this has nothing to do with this, therefore this one is one hypothesis for this. Therefore the Hofstad's inequality applies to this. Therefore the test error is a much super better estimation of the true performance of the sample. Okay, that's the reason we have a test. And however, as you said, sometimes we have multiple model families to consider. In one model family, we have some parameters that is not in the train, but outside the train, such as how many layers in a neural network, how many layers in a tree, such called hyperparameters. So those hyperparameters need to be selected as well. If for each of the hyperparameter we consider test 8, then our super nice estimation of the error band will not be as valid as we hope it to be. And therefore, we then carefully make a precious subset of test samples and use this only one. This will only be used once, only once. After we have set up everything, we put it into test here. And when this set of samples says something, says something, it is what it is. We don't change anything. It does not work. We need to start from scratch. So yeah.
Jun?
Yeah.
I have one potential solution here. What if we just pass that pass the wrong test point while predicting? So we just do a try except block, and we just ignore that test point by saying this is not in the training part. That's it. So it won't get considered. Let's say if you have 10 test points and out of those 2 are not proper, your testing won't stop. It will continue. It will just skip those incorrect points and then just continue with the 8 points out of 10 points.
Yeah, sorry, Gitas, I think your voice is a little bit overlapping with each other. Can you do that slightly slower? Sorry about that.
Okay, so am I clear now?
Better. Yeah.
Okay, so what I'm saying is, can we just skip those incorrect or the points which were not encountered by the training data set? So let's say we are using the predict function and we put a try and except block where we try predicting that specific data point. If that doesn't work, in the except we say this point is not there.
Yeah. And I get you. Yeah,
that.
this is also a
Training
solution.
won't
Yes,
solve.
you can
Testing
do
won't
this.
solve.
You can do this as well, which means you set up a default decision in the test stage.
Yeah, or maybe just ignore that.
By ignoring that, that means a default decision as well. Even you can maybe output, sorry, I don't know anything about that. It is also a decision. The decision is saying I'm not knowing, because in reality, in many applications, such as, for example, if you are controlling a nuclear plant, well, somehow you have to make some decisions continuously. You cannot just sitting back say, okay, I don't have decisions, good luck. So yeah, you in real practice, in real world applications, we usually have some backup or safe decisions to make.
Okay, so for this assignment, do you suggest would you suggest like these 3 data sets, or what Githard said as to like just mentioning that this particular sample, like we can't give you a particular decision for that sample or something like that because it's not present in the training data set for this assignment? Like, yeah.
What I said and the Gitas said, we are.
It's connected, yeah.
It's
just that
but it's not contradict with each other. You can do both or neither, whatever, because I think what you are doing is much more than what is required in the assignment. You can do whatever. So because it's not that the performance is 100% important. Even if you implement one solution by your own design, and you can just give some discussion in the report, and I think we are more than happy to see that.
Okay. Yeah, I'll be anyways also coming to the one-to-one consultation. So if there's anything I want to clarify, I'll clarify then. Thank you.
Okay, sure.
Yeah, thanks a lot.
Hey, Jim.
Okay.
Hello.
Hey, I just have a really quick question. Just from something I heard you say at the start, but I may have misinterpreted what you said. So I chose to do a perceptron training algorithm as opposed to decision tree building algorithm. Are they marked differently?
No, they are same. You mean they are marked differently? No, they are marked the same. You can choose which whatever one.
Okay, I thought maybe the decision tree got like a higher scale or something. I think I just misinterpreted what you said. As in, say with a perceptron model, you have like a less chance of getting 100% than say using a decision tree model. I don't know why I thought that, but.
You're right. You're right. Decision tree model is richer than perception model, but that will not affect the marking of your assignment. We don't mark your assignment according to the accuracy. No, we mark that according to implementation and how you have demonstrate your understanding of the algorithm.
Okay.
It
Thank
is
you.
entirely okay to have a perception which end up with a poor performance because it is a weak family of models. It's okay, yeah.
Yeah, it's just something I feel like I already started using that one, but just because I was more comfortable with the algorithms in that family rather than the decision tree.
Yeah.
I was just wondering if this was like a disadvantage or anything.
No, it's okay.
Okay,
Yeah.
thanks.
Okay. We have several people have asked questions in the chat box. Okay, I think I have addressed some of the questions. I have also people have raised your hand. Have I talked to you, or maybe we can in order? Sorry, I
Can
don't.
yeah. Can I go first? Is it okay?
Yes.
So I just wanted to share my code. I worked on perceptron algorithm from scratch, but instead of I used a similar idea, but in a slightly different manner. So I just wanted to see what all things can I work on it, because I did your lectures, tutorials, and then I used my idea of previous mathematics and ML I have learned to do this. Can you just take a look at the code if it's fine by you?
Sorry, I didn't get the last.
I'll just share my screen. I just
yes,
want
you can.
to.
Yes.
Yeah. So I just use the basic iris dataset which we have been using. Here I went for Virginica and Versicolor and worked on petal length and petal width. So initially I just used a scatter plot to because I'm just using the two, so I can just see how they are differentiated for Virginica and Versicolor. And since in perceptron algorithm our job is to determine how we can make a decision boundary to divide it. So what I did is I used a training. So instead of giving weights, I just defined weights and also built a function for that, in parallel. Then I those all things have done, sir, because I have a good idea on those. But in the testing, when I did, if I'm unable to I just did the testing accuracy and training accuracy for the data. It turns out pretty good. But when I'm drawing the decision line, I'm unable to get an idea how I particularly align it or define it here.
You are so.
Shall I go up? Shall I show you my training algorithm?
No, it's okay. But what I'm going to say is, I think your result is good enough. Why you have issue with that? It's okay. It's very good.
Actually, the thing was because now a part of the assignment is we implementing it on a practical data set also, other than this one. So I just this one is what I just studied, and I was seeing various people drawing a decision boundary, took a basic idea and used it. But I'm unable to understand how exactly do we draw the decision line using, because this part of the code is something I just referred from the internet. I understood that people do like this, and I just did it. My understanding here is very lesser compared to what I have understanding in the total above things. So I just wanted to ask how do I look into this? What is the mathematical idea or approach I can take when I'm drawing a decision boundary line?
Okay, so what those people does, or what this algorithm does is just if you look at the line number 10.
Yes.
Yeah, and 10 and 11, it it does take well, I'm showing
first column, basically all the elements of the first column. I'm just taking
no, it's doing this.
Yeah. Okay, minimum and the maximum.
So it's
I'm
just
taking-
take 2 points here, and using that 2 points, it takes a little bit slightly. This is plus 0.5, and here is minus 0.5. So basically, it takes 2 points in the data space. If you go down a little bit, yes, okay, it's fine. It takes the 2 values here.
Yes.
Okay, and for these 2 values, compute the corresponding value here defined by the classification boundary. Okay, so
Yes.
this is basically to say, okay, my x is here, which is here. Okay, x times W0 plus y times W1 plus b equals 0. That is what we have learned in class. If you remember, we have a C that, okay. So maybe I call that x1 and y, I call that x2, okay? So
Yes.
that will become x1, x2. So let me call that x1, w1, w2. So this is connected with w1. This is connected with w2, okay? And we take the sum and take consider a bias here. Let it to be 0. If this is 0, which means this is on the boundary without decision. If it is greater than 0, the decision is positive. If it is less than 0, the decision is negative,
Yes.
right? So yeah, and the purpose here is just to draw this line. Then how to draw this line? You take 1 point on this line. The point, the x1 coordinate is taken here. Okay, now you know that x1 coordinate. And what you are going to do is to find this point here. How you find this point? You need to find out the x2 coordinate. And the x2 coordinate will be, if you take this on this side, and that will be x1 w1 plus b, and divided by, because that will become x minus x2 w2. So that it will be divided by negative w2. So look,
Okay.
here will make sense, right? So
Yeah,
this is this, and this is this, and this
biases, yeah, that's the bias.
this
So basically,
negative and the negative here. Yeah. So you get the
basically
point.
I was confused with like the divided slash p weights.
Yeah.
Now I understood that we are just normalizing it. We are just normalizing
to
it.
join it. Yes.
Yeah, okay. Yeah, that then totally makes sense. Okay, because I just this plus 0.5 minus 0.5 is something I just like took it to see how the line is varying and all,
Yeah.
to just gain a basic understanding. But now it totally makes sense. I get what was trying to do. So I just wanted to ask one last query. So this is like testing with a inbuilt like what we have, like using the iris set. So should we use a practical data set also? Like if I say take the Titanic disaster problem, so should I even implement in that? Is that what we need to do?
It's extra. It's up to you. It's extra.
Okay.
So it's
Yeah.
okay.
So here is there anything else we need to add or something, or it's just that testing with the practical data set? Is that fine?
I think your implementation now is according to the requirement. Yeah. I think if you can put more efforts in discussing your implementation.
Yes. One
Sorry,
more thing.
guys. sorry, I have a back-to-back session starting from 6 p.m. So maybe can we have another people waiting? Can we?
Okay. Okay.
Yeah, maybe a quick one. Okay.
Yeah, I just wanted to ask, in this activation functions which we are taking, like, can we also take other activation functions to check, and is it necessary that we put, because I took a step function here. Can I take a sigmoid function and other functions also and put it just to see?
This is a good point. You can try other activation function, but keep in mind, if you choose other activation function, this will no longer be the original perception. This will become a mutant perception, which we will use in the next lecture.
Okay. Okay. Thank you.
Okay.
Thank you.
Okay,
So,
Jin, I'll go next. I'll be hopefully relatively quick. I just need to share my screen. So I'm going to use the digits data set.
Yeah.
But the problem with the digits, it's an 8x8, so it's 64 attributes for each pixel.
Yeah.
Technically, do you have any preference? Like, if we wanted to get that down using like either a convolution or or do a histogram of gradients to reduce the amount of attributes that's in my data set, or do a maximum or non-zero of those values. Otherwise, my equation is going to be extremely long to my x0 to x64.
You can take a relatively how can I see easier way of what I mean is you do not need to explicitly list all the attributes in x0, x1, x2. You can you can process them all together using NumPy representation of array computations. So are you using this for assignment 2?
Yes.
Okay. In this case, let me think about that. So your F0 is this. So let me.
At the moment, I've just left it as what you did, and I just got it working. But the problem is, it's getting down the attributes, which is the pixel brightness from 64 values down. I could probably get it down to maybe 6, and then just use a 6-part equation. But I just wanted to know if that's all right, if I could do some sort of convolution to reduce it down, or I was going to take the sum or the max and see if I could use those attributes.
You can. But what I'm going to say is, if you consider either the convolution, the sum, the average, the max, the mean, the contrast, whatsoever, okay, what you are doing is you take in 64 attributes, right? And you output a summary of the 64 attributes.
Yep.
Well, think about that. You take in 64, you output one number, and then you do something about this number. Then,
that's what I train the perception on. Right?
Yeah, but why not just operate on the 64 attributes from the start? Because you are going to compute something from the 64 number anyway.
Yeah, but in terms of x1 plus x2, how do I represent that sum, as an x1, x2, x3? How do I get those attributes from the array?
Can you maybe write a function such as f0? It accepts an array of 64 numbers.
Yeah. And so you compute that in the loop that trains the model. So it takes a 64, I haven't done it, but so I would take the 64-bit image, and in the actual perception training, the first bit would be to process it to reduce down the attributes.
Okay, let me have a look if I can draw something on screen. I think, interesting. I should be able to draw something here. Okay, I'm using the chat window.
Yeah, okay.
Can you scroll up a little bit so I can see the name of your variable? X, right? You have X as your variable?
Yeah.
So can you add any cell and maybe just have a look at X0?
Yep, that's X0 here.
Okay, so can we try to allocate 64 weights, such as let it to be maybe W equals numpy random dot rand 64. You can copy this into some cell. Yeah, do that.
I might just do it down here.
Yeah, you start with a new cell and now have a look at W maybe. Yeah. Okay, then open up another cell, just to type this.
Output it, yeah.
Look, by doing so, you give each attribute of X a weight. And what you can do is to take a pair of parentheses of what you are computing, give it a pair of brackets.
Which I like this.
Yeah. So if you run that, that does not change anything, which is yeah, tautology. However, okay, you can take a sum of that because now you're treating that as a one object. Look at the chat window. Yes. What you are doing now, you know what, you can make the decision of on the sum, such as in your F0, if you can make decisions according to the sum. Of course, you need to consider the normalization issue. So in this case, because all the W are positive and all the attributes are positive, so this is always positive. What you can do is you can use maybe this. You can start with something like that. Then you will start with a set of random sample weights where the weights are positive or negative, and then you can start working with perception from there.
And so when it trains that W, is it going to adjust each one of those values, or when it goes to the next step, say a value isn't in, it's negative. When it adds that value, does it just add it to all of the values in the array?
When you adjust, you remember one thing. When you adjust, you will do something like this, and this will be this thing. And now you remember the X arrow I will have the same number of numbers as what you need to adjust W.
Okay, yeah, I'll have to.
So then everything works out. I think I have to go because I have another class starts right at this minute. So please join guitar session if you still have more questions. Sorry about that.
When's the next session?
Now guitars.
Yeah,
if you go to the schedule, guitars will start another session.
Okay, cool. Thank you.
Okay, bye-bye, guys.